welcome back to another session of physical sciences. We're going to go on with the chemistry, and we're going to talk about the graphs, specifically linking our graphs to the collision theory on a particle level. We spoke about the Maxwell-Boltzmann normal distribution curve. We said last time that it's a statistical curve where we have some of our particles having a lower energy or lower kinetic energy moving at a slower pace as opposed to higher energy, higher average kinetic energy, and where we obviously have the peak in our graph. The question today is, why does an increase in temperature result in an increased rate of reaction? Now, when we first go look at the normal distribution, this is how it will normally look at a particular temperature. We see, as I said last time, this is all the particles, this particles is in motion, and this motion is determined by the temperature that these particles are exposed to. The part here is the particles that cause effective collisions. In other words, this part of my distribution curve is the particles that will form product because these particles form effective collisions. I just want to remind you again that an effective collision has got two requirements. Firstly, an activation energy that's smaller or equal to my kinetic energy. And secondly, there must be a correct orientation, meaning the electron pairs should overlap their orbitals with the correct other unpaired electrons. When we go back to the question of an increase in temperature, so if this is my particular temperature, let's say this is my normal curve. We know on the normal curve, it is a spread of all our particles at different kinetic energies starting from 0. So if we look at having, I just want to take this out, I think, so that we don't get confused there. If we look at the red curve there, this is a curve that happens at a higher temperature, at an increased temperature. Now, what I want you to see here is the peak of my normal curve actually moved to the right and it moved lower down. Now, why do we have a lower down peak? Why is the peak now a bit lower? You should remember that in this normal distribution, there is a number of particles. And in this distribution at a higher temperature, we still have the same number of particles, and these particles are actually now spread, sorry for that, these particles are actually now spread in this red curve that we see here. So what we can see now is our activation energy is actually now showing us that that compartment there is the compartment that will have effective collisions. So, if we can explain that in terms of the collision theory, we can say at a higher temperature, we have the particles that move faster on average. The particles will collide more frequently, meaning they will bump more frequently. And if we have that bumping more frequently, we obviously have more collisions per unit time, but because that particle collisions is more per unit time, the likelihood of having effective collisions per unit time is very high. So we will have more effective collisions per unit time. And if we have more effective collisions per unit time, it actually means that the rate of the reaction is high. So if we look at the graph, we can now see, as I said before, that entire part there is the particles where there's more effective collisions that happened, and that part of my graph, more than before that it was only that part that was product, I have more product that is formed because there's now more of my particles that have effective collisions. When I look at the next question, a decrease in temperature results in decreased reaction. Why does this happen? Firstly, we need to see that T1 is now showing our normal curve, and T3 is showing our curve at a lower temperature. Now we know temperature is linked to the speed, and that speed is linked to the kinetic energy. So if we look at our distribution, we now see that from the normal curve, I have a higher peak, and my peak is more to the left. So it shows you now, on average, I have a lot of particles that has a smaller kinetic energy than the particles in the original curve that we have. So when we look at the more particles, we will see there is now more particles that will have effective collisions. So when we have a decrease in our temperature, we have more particles that on average has that kinetic energy. And if we look at our blue curve, only that part of the particles will actually result in product, because only that part of the particles will have effective collisions. That is why if we look at a decrease in energy, there's a decrease in the average kinetic energy, there's a decrease in speed, so we have less collisions, less colliding with each other, less effective collisions, and therefore we have a decreased rate of reaction. We're going to move on to the next factor that we can explain in terms of Maxwell-Boltzmann as well as the collision theory. Remember, your Maxwell-Boltzmann distribution graph is all about the kinetic energy of the particles. When we look at why does an increase in the concentration result in an increased rate of reaction? Firstly, I want to remind you that when we have an increase in concentration, according to C is equal to N over V, I said to you the last time that the concentration is directly proportional to the number of moles. So the concentration is your number of moles in a given volume. If the volume is kept constant and the concentration is increased, then it basically means you have a higher number of moles compared to the concentration before. So an increase of concentration leads to an increase in the number of moles. If we go back to the Maxwell-Boltzmann, I want to remind you again that this is our normal curve, our normal statistical curve, where we will have a peak where we have our average kinetic energy for most of our particles. But when we have an increase in concentration, I said that we now have an increase in the number of moles, so the number of particles are now more than before when we had a lower concentration. So you can see if you go look at the peak here, your curve is just now a little bit bigger than before. And that bigger curve is now because of the more number of moles, the more particles that we have under the graph, in the area of the graph. So an increase in our concentration led to an increase of the number of moles, and we can see that if we look at the curve that's now a bit bigger. But now when that curve was a bit bigger, the activation energy remained the same. And this part are all the effective collisions that we have. So if we look at an increase in concentration of the reactant, we said there will now be more reactant particles per unit volume. In other words, C is equal to N over V. We have a higher concentration, so we have the number of moles are more if our volume remain constant. So we now have more particles per unit time, more particles per unit volume, and that particles is colliding all the time because there's more in that small volume, And if there's more collisions per unit time, we have a likelihood of more effective collisions per unit time, and that effective collisions per unit time leads to a higher rate of reaction. Action is then faster. So we've now dealt with the Maxwell-Boltzmann graph, distribution graph, where we looked at an increase of temperature, a decrease in temperature, and we looked at an increase in the concentration. The next factor that we're going to look at on a submicro level is an increase or a decrease of surface area. So when we look at the surface area, we have why does an increase in surface area, and now I want to remind you again that an increase in surface area means finer powder, not chunks, more powder. Why does that result in an increase in the rate of the reaction? Now, just as a reminder, I've got the same photo as before. In the first case, we've got a lump, and in the second case, we made the lump finer into powder. Remember, the bigger the lump looks, the smaller the surface area, because the surface area is actually the contact area where our collisions take place. So when we look at a powder, there's more contact area. So for a powder, we have a larger surface area. So when we look at our Maxwell-Boltzmann graph, we will see that we have the normal graph. And because of the surface area that's now increased, we now have more particles or more interaction on the bigger surface area. So when we use powder, we actually now have more particles that interacts during the reaction. We have more particles that actually has that average kinetic energy. And if we go look at how many particles will actually result in effective collisions, we can see that entire part there result in effective collisions. So, with the collision theory, we can then now say an increase in surface area will increase the rate of the reaction, because the larger the surface area, this is the contact area, the more particles are involved in the collision. So more collisions per unit time, more effective collisions per unit time, and that leads to a higher rate of reaction. The next factor that we will look at is why does an addition of a positive catalyst result in an increased rate of reaction? Right. Want to remind you that a positive catalyst is a substance that does not take part in the reaction, but it does speed up the reaction by lowering the activation energy. So if the activation energy is lowered, it basically means it is an alternative route that can be followed. So a positive catalyst lowers the activation energy of the reaction, and it provides an alternative route or an alternative path, meaning that product will be formed faster. Remember, not more product, just faster. So there will be more collisions per unit time. There will be more effective collisions per unit time, and that will lead to a faster rate of reaction. We go look at how the positive catalyst will be shown on the Maxwell-Boltzmann distribution. Remember, it lowers the activation energy. So if we go look at our axis here, our kinetic energy on the x-axis, we can now see that the activation energy now moves a little back on the axis to a smaller number. So all these particles there will result in effective collisions per unit time. Right. And in summary, we are now almost at the end of our lesson. I just want you to make sure that you can always interpret your graphs. Remember, you have different graphs that you're looking at. You must be able to interpret it, know and understand conceptually where it fits in. You must be able to apply the definition of rate of reaction to graphs. And remember, you also will link that up to the collision theory, that graphs will be linked to the collision theory on a sub-micro level, and that is where you will talk about more effective collisions per unit time, faster rate of reaction. So you need to bring that back and link it to the graphs, and obviously for rates of reactions, you must try and always recall the factors that affect the rate. So there are 6 factors, and that brings us to the end of our session. Thank you so much.